So hi guys, I'm Preeti, and I'm doing my project on Stack Overflow, and I work with Professor Dewan and Jacob Bartel. So most of you know what Stack Overflow is. It's basically a site where you can post computer programming questions and get them answered. So we encountered two kind of interesting questions with regard to Stack Overflow, and that's the question of liveness and speed. So really our desired goal is to be able to have a program automatically tell us how long it'll take us to get an answer, either whether or not it's our earliest answer or the first acceptable answer. And no previous work has actually had this goal before, so we're the first ones tackling this. But here's what previous work has done. They've looked at factors influencing both features all across the board, with respect to IM, email, social networking. But they haven't looked at Stack Overflow, and they also haven't looked at speed prediction. So we wanted to see which of these factors actually apply to Stack Overflow at all. So the first thing we looked at was the length of post. And when we look at social networking domains, it's limiting the number of sentences actually tends to create faster responses. So when we tried to look at this created a bit of a problem, because in most message bodies on Stack Overflow, you have these huge chunks of code that you can't really translate into sentences. So how do we tackle that? Our solution was, instead of looking at the message body, just go look at the title. Because anyway, people decide to whether or not to answer or view a question based on what the title is, and not what the message body is. So we looked at the number of words in the titles, and we found something kind of interesting. So this is not a histogram, this is a scatter plot. Some people have gotten confused over this. We see that the distributions of elapsed times actually change pretty systematically. And upon close inspection, if you take the medians, the 50th percentiles of all these distributions, they actually correlate quadratically with the title lengths. So this is actually one of the features we used in predicting answer times. So other features we looked at, we had less success. Keywords and punctuation. Some studies have found that using certain types of pronouns lead to a higher probability of responses, but we found that neither presence of punctuation or keywords had any significant effect. And the same applied to things like time of day and day of week. So this is basically this is a summary of all the features that we looked into, and title length was the only one that had any significant correlation. So consequently, we used title length in our prediction of response times. And the other thing we tried to consider was tags. So the intuition behind using tags is that, what happens if you gear a question towards a specific community group? Do specific people with, more concentrated interests tend to answer faster? So we looked at features, now we have another question. So how do we actually use these features in our prediction? So we can consider two different scenarios, one in which we use these features, and one in which we don't. And we're only considering, distribution-based approaches, and we'll kind of see what that means in a moment. So we have, if we take the most obvious approach possible, it's to take one constant value and predict it all across the board, regardless of what any other information you have. So this is what we did first. We just took the mean and median values for both accepted answer elapsed times and earliest answer elapsed times, and just predicted them constantly throughout the entire test data set. But this isn't a very intelligent approach at all. So can we do anything better? And this is the approach that we proposed, and it's to partition the entire time range into bigger blocks and predict that a question will be answered within a time range rather than pinpointing a specific prediction time. So we have different options as to how we partition the entire time range. So this is one option that we had. We can do constant time partitioning. So this is where you fix a specific duration of time and create time ranges as such. But we run into lots of different problems and questions. Number one, how many blocks are we separated into? And number two, these time differences aren't necessarily absolute. For example, if you have time range sizes of 10 minutes, the difference between 10 minutes and 20 minutes is much more significant than the difference between a year and 10 minutes and a year and 20 minutes. So we want to take those differences into account. So unequal time ranges are probably more appropriate. So now going from here, how do we split these up? So one approach that we considered trying was to statically define these time ranges. So we have common notions of minutes, days, hours, days, weeks, etc. But these change from user to user. They're quite arbitrary if you try to program, hard code them in that way. So instead, we can take a dynamic approach that's guided by the data set. This is exactly what we did. So we used k-means clustering on along one dimension to create these different time ranges. And consequently, for example, these are the time ranges that we got for accepted answer response times. And I'd just like to point out that a previous study has actually had a similar result in the first time range. That is that most questions tend to be answered between 11 and 20 minutes. So that was kind of interesting to find out. So now we have all these. We have our time bins now. So how do we go from here? So again, we have a pretty obvious approach. So instead of taking the mean and median times, just take the mean and median time ranges and predict them again. But we actually have a better option now, and that is to take the most frequently used time range and predict that all across the board. So we have constant time range prediction schemes, but it doesn't really introduce any concept of variability in prediction, and that's something we want, especially considering that some time ranges will never get predicted at all, no matter what. So we can introduce a probabilistic scheme. We can call this a roulette wheel scheme, or we can call this a weighted random choice scheme, and that is to draw probabilistically from the existing distribution of times we already have. And the nice thing about this approach is that it presents us the opportunity to actually use the features. So this is the approach. Instead of uniformly predicting the most frequently occurring time bin, we can vary the time bins that we predict based on their probability of occurrence. And now we have variants of these. So we can make a decision about the distribution of times we use based on which tags are present, and even upon which title lengths the questions contain. So these are basically our methods. So let's see which one did the best. So in terms of evaluation metrics, this is the metric that we basically use, relative error. And this metric actually guarantees us the largest possible error. So we're not really cheating ourselves by picking out a small error than we actually should be. So we can consider first the case of the time till our accepted answer, and these are the baseline. These are histograms of relative error, and these are our baseline approaches. What happens if we pick the mean time and predict that constantly, and the median time, and so on and so forth. And these approaches don't do very well. There's a huge spike at 100% relative error, and that's not good at all. So if we compare that to our best approach, so our best approach surprisingly turns out to be just taking the maximally occurring time range and predicting that uniformly across all questions. So it was surprising that we didn't really use any features at all, and it actually gave us a pretty good result. Above 50% of the questions happen to be predicted with near 0% relative error. And that wasn't actually the case with the time till the earliest answer. Again, here are our baselines. They look pretty similar to the baselines for the accepted answer elapsed times. Again, they're not very good. But in this case, our best approach turned out to be to use the title lengths in the probabilistic approach. This was a very surprising result, especially considering that when we use the most frequently occurring time range approach when trying to predict earliest answer times, it actually got a lot worse. So now we come to our conclusion. So it was interesting that title lengths were the only features that correlated at all with elapsed times, and dynamic time ranges actually work a lot better than pinpointing predictions. So in terms of future work, when we used tags in our time prediction, we were limited to the top 100 tags, but in reality there are thousands of them. So one of the things that we're looking to do is cluster them into larger community groups to reduce the dimension of our data matrix for prediction. Yeah.
Questions for people?
Yes.
Did you look at who the individual posters were, if their questions have been answered fast in the past?
So we did. Was found that there wasn't really an association there. Yeah.
What other attributes of the poster?
The attributes included, how many so you had access to the number of questions that were posted by that user. You had access to the status of the poster, whether they were, a student, experienced, a mod, anything like that. But they didn't really show any associations.
Other questions? Thank you, Preeti. Okay, so our last presentation, we had a scratch.